Hello, and welcome back again to the course on physics for engineers. We are still on the last chapter of this course, which is all about optics. So let us first review some concepts before we proceed with this lesson. So in the previous lesson, we actually have discussed about the two basic phenomenons in the propagation of light, reflection and refraction. So in a material, in general, reflection and refraction can happen simultaneously. So light can be bent back away from the medium, or it can bend through the medium. So the law of reflection states that the angle of incidence is just equal to the angle of reflection. And the law of refraction, or Snell's law, states that basically the angle uh, depends on the depends inversely on the index of refraction. So in this case, uh, this medium here has a higher index of refraction. It will have a smaller angle. So for this lesson, we will be talking about uh, TIR, polarization, dispersion, and scattering. So another phenomenon involved with reflection is what we call total internal reflection. So this is a phenomenon where there's no refraction happening when the angle of incidence is greater than a certain critical angle. And this critical angle is given by the sine inverse of the ratio of the index of refraction. So for example, in this case, when the angle of incidence is less than the critical angle, there will be refraction, and actually there will also still be reflection. But when the angle of incidence is equal exactly to the critical angle, there will be no reflection or refraction. The light will actually be parallel to the boundary. And when light is greater than the critical angle, there will be no reflection or refraction, sorry. There will only be total internal reflection. So that's what we call total internal reflection, no refraction. Now, this can only happen when the light is incident on a medium of higher index of refraction. So the assumption here is that the medium A has a higher index of refraction compared to medium B, or the medium B has a lower index of refraction as compared to medium A. So TIR can happen, say, from when light travels from water to air, but it cannot happen when light travels from air to water. It can only happen when light is an incident on a medium of higher index of refraction. So when light goes from higher index to lower index of refraction, that's the only way that total internal reflection can happen. So here is a PhET simulation which describes reflection, refraction, and total internal reflection. So normally, in a boundary, so this is from air to water. So let's change this from water to air. Water to air, for instance. Okay. So normally, there will be always a reflected light and a refracted light. But there are certain, you will notice that there's a certain angle of incidence. There's a certain angle here wherein you will notice that there's a critical angle wherein the refracted light vanishes. And beyond that angle, it's only total internal reflection. So beyond this angle, it's purely reflection, as if this boundary here becomes a mirror. And that is the phenomenon called total internal reflection. So in this example, this is from water to air. Again, TIR, or total internal reflection, can only happen when light is coming from a higher index of refraction towards a lower index of refraction. So when the angle is less than the critical angle, there will be both reflection and refraction. But beyond a certain critical angle, it's purely total internal reflection. It's as if it becomes the boundary becomes a mirror. Okay, so that's TIR, or total internal reflection. So applications of total internal reflection is, say, in fiber optics. So in fiber optics, light travels through the optical fiber and it's totally internally reflected in the boundaries. So light travels uh, in a fiber optic by means of TIR, or total internal reflection. And this actually gives us a faster internet as compared to copper cables. So in a diamond also, there's also total internal reflection. So that's actually uh, what makes the diamond brilliant. It's because of total internal reflection. How diamonds are polished. So diamonds are polished or cut in such a way that there will be total internal reflection on their back surfaces. So you will see now the diamond as reflecting from the uh, back surfaces by virtue of TIR. So there can also be a total internal reflection in a poroprism. Poroprism are usually used in binoculars. So that's also total internal reflection. So in this side here, this boundary here, light actually becomes is bent uh, in such a way that there will be no light leaking there. So it's purely reflection. So another phenomenon related to refraction and reflection is polarization. So polarization refers to the transverse property of light as an electromagnetic wave. So all transverse wave can actually be polarized, including an electromagnetic wave. So an electromagnetic wave is a transverse wave, so it can be polarized. So natural light is actually unpolarized light, or basically it's polarized in all possible direction. That's natural light. So in this case, this is natural light. Its polarization is in all possible direction. Now, this is an example of light that is polarized along the vertical direction, or along the y-axis. This is an example of light that is polarized along the x-axis. And this is an example of light polarized in an xy direction. So when you use a polarizer, or sometimes we call that a polarizing filter, it actually just only permits light with certain polarization direction to pass. So for instance, in this linear polarizing filter, if you have unpolarized light or natural light with polarization in all directions, when this light enters this polarizer or polarizing filter, only light with the same orientation as the polarization of this filter can pass through. So in this case, the vertical component, or the vertically polarized light, can enter this polarizer and exit this polarizer. So after, that's how you polarize light. So polarization, unpolarized light actually causes unwanted glare. So if you have a non-polarized and a polarized shades, for instance, uh, a polarized uh, sunglasses will actually look more clearer, because you just see one light basically in one direction. Unlike in unpolarized sorry, glasses, you see light in all possible directions, and sometimes it causes unwanted glare. It's too bright. So that's the effect of polarizer. So for instance, in this case, if you have a light that has two polarizations, when it enters this filter, only the vertically polarized light can pass through. And when it enters this another filter, where the polarization direction that it will allow is just this one, then there will be no light passing through this uh, series of two polarizing filters, since no light matches the polarization requirements or restrictions of this second polarizer. So that's basically polarization. Now, you can also polarize light without using a filter, by just purely reflection. So this is what we call polarization by reflection, and it happens at a certain angle called the Brewster's angle. So the Brewster's angle, theta p, the polarization angle, is given by the tangent inverse of NB over NA. So in this case, the reflected light becomes 100% polarized, and its polarization is actually parallel to the surface or to the boundary. So the polarization, you have natural light, incident light is unpolarized or natural. It's basically, when you say unpolarized, it has polarization in all possible directions. And when it's reflected, there will be purely polarized light in one direction parallel to the surface. And then you have refracted light that is partially polarized. So that happens only at a specific angle. And sometimes it produces unwanted glare. And this is actually the reason why polarizing filters are widely used in sunglasses. The reason why we have sunglasses with polarizers is because of this polarization by reflection. So usually, the manufacturer of sunglasses orient the polarizing filters vertical, vertical, so that the polarized light that you see uh, will be reduced. So you get rid of the unwanted glare. So you make the light hitting your sunglasses and exiting your sunglasses towards your eye be as not as bright as possible. So this is an example of polarization by reflection. So I think you have noticed this when you look at a car window or we look at the rooftop of your neighbors. There's a certain angle where there is a very bright, very bright and focused light, like a laser light, and that angle is due to polarization by reflection. So if you use a filter, so this is without a filter, seeing this car window without a filter, and now seeing this window without, also with a polarizing filter, with the sunglasses, for instance. So a sunglasses is an example of a polarizing filter. And you will see that the glare is removed when you see a filter because it only uh, allows certain polarization directions. So you remove the unwanted glare. So sometimes polarization by reflection is unwanted. Sometimes we don't want polarization by reflection. That's why we use sunglasses. Okay, the next phenomenon is called dispersion. This happens when white light is split into colors, such as when white light hits a prism. So white light is basically just a composition of all the visible wavelengths from violet to red. Now, if you will recall from the discussion on the index of refraction, uh, the wavelength is actually directly proportional to the speed of light. So, meaning red light is actually faster than violet light. So, when a white light hits a prism, the first to exit is the red light, and the next to exit will be the orange, yellow, green, and the last to exit will be the violet light. So what happens with white light, even though it contains all of the colors, but red will exit first because red is faster than violet. So this is the phenomenon called dispersion and commonly known as the rainbow. So uh, if you have a rainbow, basically a rainbow happens when sunlight, white light, hits a water droplet. So sometimes rainbows can be seen after a rain. So in order to see a rainbow, there must be sunlight behind you. So that's the if you are here, if the person is standing here, then the sun must be behind him, and the water droplets, the rain, must be in front of him. So that is the arrangement in order to for you to see a rainbow. Sun, the person, and then the water droplets or the rain. So if that is not the arrangement, you can't see the rainbow. So the water droplet is refracted, totally internally reflected, and then dispersed. So dispersion is basically uh, a combination of reflection, refraction, total internal reflection. and then you see dispersion. So, and what you see will be a rainbow. Now, the last phenomenon involved in the propagation or traveling of light is scattering. So, scattering is basically involved in absorption and re-emission of light by all materials. So, all materials absorb and re-emit light. For example, my t-shirt looks yellow because it absorbs white light. White light hits my t-shirt and then it absorbs the other colors except for yellow, where it re-emits the yellow. So basically, that's how you explain colors. It's basically white light hitting your, say, my shirt. It absorbs all of the colors except for yellow. It re-emits the yellow color, and you see a yellow color of my shirt. So blue light is actually scattered 9.4 times than red light in the sky. That's the reason why the sky is blue. So blue is more intense than red light, especially during noontime. So during noontime, uh, blue is actually scattered to us, and that's the reason why the sky is blue. Now, during sunset, around 5 or 6 p.m., most of the blue light are scattered and only the red light remains. That's the reason why you see the sky as reddish or something like of an orange. So because blue light is scattered, is now more scattered, and only the red light remains. Red, orange, yellowish light remains. So that one. The reason why blue is the sky is blue is because of uh, our atmosphere scattered scatters blue light 9.4 times more than red light. So if you are searching for another planet, for instance, its atmosphere, if you want the atmosphere to be the same as our atmosphere, then that atmosphere uh, can or must or should look blue, because uh, it can mean that it has the same composition as our atmosphere. So our atmosphere scatters blue light more as compared to red light. So clouds, on the other hand, they look white because the water droplets, again, clouds are just water vapor. The water inside the clouds scatter light in all wavelengths. So when all of the wavelengths are visible wavelengths are present, red, orange, yellow, green, blue, violet, then you get white light. So that's the reason why clouds look white, because they scatter all of the wavelengths, all of the colors equally. Unlike the our atmosphere, which favors blue more, and that is has something to do with the composition of our atmosphere. So let's have an example. So this is an example on total internal reflection. So sometimes when you see the bottom of a glass, you see your reflection, and that is actually the phenomenon called total internal reflection, where the bottom of the glass becomes uh, 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 like a mirror. So you look at the bottom of a glass filled with water, and notice that there are certain angles that the bottom surface becomes a mirror. So that is the glass boundary reflects only light. So the boundary that we're talking here is the glass and water boundary. Again, total internal reflections happens only uh, when light is incident from a higher index of refraction. In this case, glass has a higher index of refraction compared to water. So it's from glass to water. So at what angle does, with respect to the glass-water boundary, does the boundary become a mirror? Assume the index of refraction of glass is 1.52. So for water, it's 1.33. So we solve for the critical angle. Sine inverse NB is water. Na is glass. So Na 1.33, NB is 1.33, the water. Na is glass 1.32, and we get the critical angle is 61.04 degrees. So in order for TIR to occur, the angle of incidence must be greater than 61.04 4. So again, TIR only happens when the angle of incidence is greater than the critical angle. Okay, so let's have another example. So this is now polarization. We use the same example, but now polarization by reflection. So at what angle will light from the air will be polarized by reflection from the air glass boundary? So by the way, unlike TIR, total internal reflection, which requires that for it to occur, it must be traveling from a medium of higher index of refraction to a lower index of refraction. For polarization, there's no restrictions like that. It can travel from a lower to a higher index of refraction, or light can travel from higher to a lower index of refraction, and the reverse. So here it's from the air. We are now talking about the air glass boundary here. So the polarization angle is just tangent inverse of NB over NA. Our NB here is glass. Our NA is air. So it's now from we're now talking from air glass boundary. So air is 1, NB glass is 1.52. So therefore, the polarization angle is 56.66 degrees. So in this specific angle alone, will the light from the air reflected reflected in the air glass boundary will become polarized, or will become glaring. Okay. So but only at that specific angle. Unlike in TIR that there are many angles, because it's greater than the critical angle, and that's a lot of angles. So that is the end of the lesson on propagation of light. So basically, the two main phenomena is reflection and refraction. So then you have TIR, polarization, dispersion, and scattering. So in the next lesson, uh, the next 3 lessons will actually be the focus of this chapter, which is all about geometric optics. So when you study geometric optics, you study actually image formation in lenses and in mirrors. So I will see you again in the next lessons.